Greetings, Global Impact students. This is Mr. Ellinger. This lesson is on families of functions. Our learning target for the lesson is we want to be able to analyze transformations of functions. Some essential understanding for you from this lesson: there are sets of functions called families, in which each function is a transformation of a special function called the parent. A parent function is the simplest form of a set of functions that form a family. Each function in the family is a transformation of the parent function. Some background knowledge that we need for this: there are two classifications of transformations we need to remember. The first are rigid transformations, called this because the original shape of the graph does not change, only its location, and these are translations, reflections, and rotations. We also have non-rigid transformations, which do change the shape of the original graph: stretches, compressions, and dilations. Okay, so there are sets of functions called families, like we said, in which each function is a transformation of a special function called the parent. The linear functions form a family of functions. Each linear function is a transformation of the function y equals x. So the function y equals x is the parent linear function, and every other linear function that we study is based on this parent function y equals x. A parent function is the simplest form in a set of functions that form a family. Each function in the family is a transformation of the parent function. One type of transformation is a translation. A translation shifts the graph of the parent function horizontally, vertically, or both, without changing shape or orientation. For a positive constant k and a parent function f of x plus or minus k is a vertical translation. For a positive constant h, f of x plus or minus h is a horizontal translation. So you can see here, if we want to translate vertically, we take the function and we add or subtract some constant. If we want to horizontally translate a function, then we change the input value of the function, so f of x plus or minus some constant. So here we have an example of a vertical translation. The red curve here is the parent function. If we add some constant k, it shifts the graph up. If we subtract some value, some constant k, it shifts the graph down. Horizontal translation, again, our red curve in here in the middle is our parent function. If we add some h value to x, it shifts to the left. And if we subtract some h value, it shifts to the right. And this is a little backwards. You might think that if we add a value to x, it should shift it in the positive direction, but it actually works the opposite. Okay, so how are the functions y equals x and y equals x minus 2 related? How are their graphs related? One way we could analyze this is to just make a table of values. Here are our x values, here are the y values that go with the equation y equals x, and here are the y values for the equation y equals x minus 2. Each output for y equals x minus 2 is 2 less than the corresponding output for y equals x, and that makes sense because we're substituting in x, we're subtracting 2, that's going to give us output values that are 2 less. The graph here in this black line is y equals x. The blue line is y equals x minus 2. All right? So y equals x minus 2 is the graph of y equals x translated down 2 units. Now what you'll notice, we can discuss the slope of the two lines is 1. So the lines are going to be parallel. So when we translate lines vertically, horizontally, they're going to be parallel to one another. They're going to be parallel to the parent function. The only thing that changes is the y-intercept. What is the graph of y equals x squared minus 1 translated up 5 units? Well, to translate the graph of y equals x squared minus 1 up 5 units, to get the blue parabola on the graph, the equation of the parabola is y equals x squared plus 4. What we do is we take y equals x squared minus 1 and we just add 5 to it. So that's y equals x squared plus 4. And we have a table that demonstrates that, and we have a visual on our graph to represent that as well. Okay? Arrow showing the upward translation. So here we have an application. The graph below shows the projected altitude f of x of an airplane scheduled to depart an airport at noon. That's the black graph. Okay. If the plane leaves 2 hours late, what function represents this transformation? That's going to be the blue graph. The 2-hour delay means the plane leaves at 2 p.m. This shifts the graph to the right 2 units. The function f of x minus 2 represents this transformation. So in our new function f of x minus 2, when x is 2, it has the same function value as the black function, the original function, when x was 0. Okay, so we have to subtract 2 from all these x values to get their y values to correspond with the original parent function. And that's why it's a little backwards, okay, because the shifts horizontally, if we want to compare function values back to the parent function, we have to subtract when we've shifted to the right to get those same values. And if we were to shift to the left, we have to add to get back to those same values. So suppose the flight leaves 30 minutes early. What function represents this transformation? What does that do? The 2 in the original, or in this function up here, represents 2 hours, right? 30 minutes is half an hour. So our function would be f of x plus 0.5, or 1/2. We could write it this way. But the graph would definitely be shifted this direction, right? So a horizontal shift to the left, we have to add values to the x, the translated function. A reflection flips the graph of a function across a line, such as the x or y axis. Each point on the graph of the reflected function is the same distance from the line of reflection as its corresponding point on the graph of the original function. When you reflect the graph in the y-axis, the x values change sign and the y values stay the same. So here we have our parent function, this black graph. When we flip it over the y-axis, we get this green graph. And as it says, the x values change signs, the y values stay the same. Okay, so for instance, this point here and this point here, they have the same y value. The only thing that changes is the sign on the x coordinate changes, positive to negative. When we reflect a graph in the x-axis, the x values stay the same and the y values change, because when we flip over the x-axis, we are having a vertical change. So here's the x-axis, so our point 1, 1 is reflected to 1, -1. So the x-coordinate stays the same, the y value changes sign. For a function f of x in general, the reflection in the y-axis is f of -x, and the reflection in the x-axis is negative f of x. So what that means is if we take our parent function and we reflect it y-axis, we get new function values. Or what we do is we evaluate the function for a sign change on -x. When we take the parent function and we reflect it across the x-axis, the change is the output values of the function. All right, over here we have an example. Let g of x be the reflection of f of x equals 3x plus 3 in the y-axis. What is a function rule for g of x? Well, we know that g of x is going to equal f of -x. G of x equals f of -x. So f of x is 3x plus 3. What we'll do is we'll evaluate the function f for -x. So we'll put -x in for x, and we will evaluate this. So 3 times -x is -3x plus 3. So you can see what we're doing here is we are generating a new function g by evaluating f at -x. So here was f of x. Take out the x, put in a -x, and you've got your new function g that's based on the parent function f. Okay, a vertical stretch of a graph multiplies all y values of a function by the same factor greater than 1. A vertical compression reduces all y values of a function by the same factor between 0 and 1. For a function f of x and a constant a, y equals a times f of x is a vertical stretch when a is greater than 1, and a vertical compression when a is between 0 and 1. And here we have, on our graph, the blue curve is our parent function f of x. right? If I take some quantity A, okay, greater than 1, and I multiply it by f of x, you can see what it does to the graph. All three of these graphs share some points, but for different x values, we get a much taller graph, if you will, stretched out. Okay, on the green graph, when we multiply f of x by 1 over a, some fraction less than 1, we get a shorter graph, if you will. It's compressed, right? So that's what it looks like, a stretch versus a compression. So here you have an example. The table at the right represents the function f of x. What are corresponding values of g of x and possible graphs for the transformation of g of x equals 3 times f of x? Here we have a table with our x values and our f of x values, and that is the red graph below. And if we multiply each value of f of x by 3 to find each corresponding value of g of x, this is our table. So we have our x values, we have our f of x values. 3 times those f of x values, we get these new values of g. So what we're going to do is we're going to take negative 5, 6, negative 2, 6, 0, negative 9, 3, 3, and 5, negative 6, and plot them, and we get this blue graph. Okay, so the blue graph is stretched out. All right, so here's a summary of what we've talked about here with vertical translations, vertical stretches and compressions, horizontal translations, and reflections. These are essential things to have in your notes. You will refer to these often. Make sure you get them written down, and we'll see you next time. Have a good day, folks.